In this video, I'm just going to give you a few basic approaches to evaluating limits and also underlie some of the properties of limits that you can utilize. So in this first one, it says with the limit as n goes to infinity of 1 over n squared, you can see that as n gets bigger, this fraction gets smaller and smaller, so it's reasonable to assume that that's going to go to 0. Now the second one here, the limit as n goes to infinity of 4n squared plus 2n minus 1 over n squared plus 1. There's a couple ways to approach it. One way that's often used is to make it really clear, is to divide every single term of the expression by the highest power, which happens to be n squared. And in doing that, it becomes very clear. You sort of almost using what you came across in part A to get the answer. So in terms of like showing your work, this is one thing that people will like to do. So I'm taking every single term in the expression and I'm dividing it by n squared. And if you simplify this, you get 4 plus 2 over n minus 1 over n squared divided by 1 plus 1 over n squared. And in doing that, as n goes to infinity, we can see that that goes to 0, that goes to 0, and that goes to 0. Right, which suggests that the whole limit goes to 4 over 1. That's one style. Another style is to do what's called an n behavior model, which is to say that as n goes to infinity, 4n squared plus 2, so I'm going to put an or here because either one of these is fine. In the long run, this is behaving like, so again, I'm not saying that the expressions are equal, I'm saying that the limits are equal. In the long run, the numerator behaves like 4n squared and the denominator behaves like n squared, and those cancel, and so you just get a 4. So either one of those approaches is fine. And as a third example, I've got the limit as n goes to infinity of these two expressions being added. I really should put that in brackets. I'm using this just to highlight two properties you can use of limits. So the first thing I might do is I'm going to factor out a 2 here. So that's 2 times 1 over 3 to the n plus 4/5 to the n. And then the next thing I'm going to do is the limit of a sum is the sum of the limits. So I can write this as the limit as n goes to infinity of 2, and I'm going to write this as 1/3 to the n, plus the limit as n goes to infinity of 4/5 to the n. So that's one property of limits. You can just find the sum of the limits individually. So this 2 can come out. That's another property that's useful. Constants can come out. All right, and now we'll just use our understanding of geometric sequences. We know that both of these expressions here, 1/3 to the n and 4/5 to the n, those are geometric sequences in which the r value is less than 1. So we know that these go to, we know that these go to 0. So this is going to be 2 times 0 plus 0, which is 0. So there's some basic properties you can use. This limit's important because it's meant to exemplify just how quickly factorials grow when compared to exponentials. And it's to get you to see that we are on firm ground when we make the claim that factorials grow faster than exponentials. So just to give you one example of why that's true, let's just look at the first 14 terms here. So I'm actually going to write them out. I'm going to write out all 14 fours here. So just bear with me. So there's 14 fours. And 14 factorial would look like this. 1 times 2. I'm going to line them up as best as I can. right? So it may seem obvious to you that the denominator actually is bigger than the numerator, but let's be very, very, let's really try to persuade someone who's not sure. The way you could do that is just kind of go term by term and show that you can rearrange the bottom so that each term in the bottom will always be bigger than its partner above on the top. So the only real problem we have is beyond this point, right? I'm sorry, before this point. Before this point, the first four fours are bigger than the 1 and the 2 and the 3, or at least in the 4, or at least bigger than or equal to. But after that, we know that the terms in the bottom are bigger. But with a little rearranging, we can fix that. So I'm going to take a 2 out of this 14 and leave behind a 7. And by doing that, I'm just going to kind of bring it over here with this 1. So I'm going to take that 2 and bring it there with the 1. So now that's a 2. I'm going to take this 12, I'm going to take out a 2 and leave behind a 6. I'm going to take this 2 that I first wrote down and I'm going to turn it into a 4. So if you think about what I've done, I've really just kind of made them even. And that's good enough for now. So I'm going to use the sideways inequality. That's bigger than or equal to 4. Now let's do with this next one, this 2. I'm going to take a 2 out of this 10, leave behind a 5, and multiply by this, and I get a 4. Alright, so now I can claim that the bottom is bigger than or equal to the top in that instance. And I can take out, I can take out a 2 from this 8 here, leave behind a 4. And now this becomes a 6. And that is definitely bigger than, the 4. And now I've kind of done it, right? Because if you just go down the line, I can say that the bottom, term by term, is either bigger or bigger than or equal to the top. Okay, and so the point is that this can be done, especially as n gets bigger. We stopped at 14, right? And this rearrangement and sort of borrowing of factors here, imagine if n is really big, right? If n is like 100, then clearly we'll have more than enough factors to borrow from the end to bring over to the front and clearly state that the denominator is bigger. So what you want to take away from this informal example is that n factorial grows faster than not only 4 to the n, but x to the n for all x values. Okay, so therefore this must be 0. Okay, so use that as just kind of an informal understanding of why we can say factorials outstrip exponentials, and that'll help us evaluate limits. As another example, let's take a look at 12 to the x divided by x to the 12th. And numerically, I just want to, I'm going to use some data here from Desmos, and just to show you that if we go all the way to the 20th, 12 to the 20th, and divide that by 20 to the 12th, right? Some people may not have a good sense of which one will be bigger. So let's just look at a numerical. So this is about, I'm going to say about equal to, only because the terms got so big that even Desmos had to round. So 12 to the 20th, if we look at the top chart, is 3.83376 times 10 to the 21st, whereas 12 to the 20th is 4.096 times 10 to the 15th. So we can see that even just by the 20th term, the numerator is much bigger than the denominator. Okay, so the power of exponentiating is will dominate this polynomial in the bottom, x to the 12th. So we know that the numerator is growing bigger here, which means that this goes to infinity. And we'll use this as a source for this statement, which is that exponentials of the form a to the x, where a is bigger than 1, grow faster than polynomials. So couple that with the last example, and we kind of have a little hierarchy here. We've got that factorials grow very, very fast. Exponentials grow not as fast as factorials, but faster than polynomials. And this understanding is going to help us in evaluating limits of quotients.